Okay, let's take a look at what a limit is. So a limit, written as limit as x approaches a of a function f of x, is basically when you're trying to gauge what value y is going to approach when x approaches a value a, right? And this is really useful when we're looking at if a function is continuous or not. A continuous function basically will have no breaks in the function. So you can basically draw the function continuously without lifting your pen. That's how they usually define this. So we're going to look at what a break is, but breaks include what we call discontinuities. A break will basically include what we call a removable discontinuity. And we'll take a look at all of these in a graphical manner, which represents a hole, right? A hole is basically a point that doesn't exist on the graph, right? We can also take a look at another type of break is an infinite discontinuity. Right, an infinite discontinuity is really it's commonly found in a vertical asymptote, as well as a jump discontinuity. And jump discontinuities are common in piecewise functions. So I'm just going to illustrate what these breaks represent, how you can kind of draw these out. And we're going to take a look at how limits can be utilized to determine or assess continuity in a function. Let's take a look at a removable discontinuity, also known as a hole, right? So here's an example of a removable discontinuity. And you can see that there is a point that's missing here, right? So this is an example of a discontinuity in a function. So this is a function, whenever you have a discontinuity in a function, then you can say that this function, let's call this guy f of x is discontinuous, right? And it just takes one break in the function to make it discontinuous, right? And let's say that this function is discontinuous at a certain point. Let's call this a, and let's call this like f of a or something. Okay, so it's discontinuous at this point, right? So this is an example of a removable discontinuity called a hole. Right? Now the other type of discontinuity that we're going to be talking about is called an infinite discontinuity. So I'm going to show you guys that. So for an infinite discontinuity, I'm just going to erase this and show you guys that. For an infinite discontinuity, you basically have a vertical asymptote, right? So this is what it will look like. Let's say that we have a curve that looks like this, and another curve that looks like this, right? This is really similar to our reciprocal function, right? And the infinite discontinuity occurs at the y-axis when x is equal to 0. Okay, so this is where the vertical asymptote is x is equal to 0. Okay, so we have an infinite discontinuity when you have a vertical asymptote. Okay, so this also represents a break in the function. So this is also an example that is discontinuous. Okay, so we'll talk about these examples in more detail as we go on. Okay, right, so this is an infinite discontinuity. Let's take a look at the third discontinuity. It's called a jump discontinuity. Just gonna draw that out here. Right, and a jump discontinuity is really common in piecewise functions. Let's say that one part of the graph looks like this, and the other part of the graph looks like that. Right? So one point here is missing, another point is continuous. Let's say that this is some value of a, or some value of x, right? We'll call this a. Right? So we have a point that is missing, right? So this is f of a would exist here, but this guy would not exist. And you can also see that there's a break in the function here. Okay, so once again, a continuous function is basically a function where you can draw it without lifting your pen. There are no breaks, which include removable discontinuities, infinite discontinuities, and jump discontinuities, right? So this guy here was an example of a jump discontinuity. We're going to take a look at this later. Okay, and in order to assess continuity, we can actually look at the limits. So going back to our description of limits, I'm just going to erase all of this. Right? We can express a limit of a function f of x and pretend f of x here is y. Right? So you can think about it as limit as x approaches a, y. We can express a limit of a function as when x approaches a, y will approach a certain value L. Okay? And L is some kind of finite value. Okay? For that limit to exist, L will be a finite value. If L is equal to positive or negative infinity, this is not a finite value. Okay? And if L is equal to positive or negative infinity, that means that the limit doesn't exist. Okay, so D and E for doesn't exist. Okay, so I've written down some criteria for when limits will exist, right? So limit as x approaches a of f of x exists if the following three criteria are met, right? And basically, the limit should always equal a finite value. So let's say limit x approaches 3 of f of x is equal to 5. Okay, this is a finite value, right? Now, if this is our graph, and as x approaches 3, and let's say this is 3, is equal to 5, and let's say that, you know, this is some value here. Okay, this is like 0 and 2, and then this point here is 5. Okay. So that means that if limit x approaches 3 of f of x is equal to 5, then the point 3 and 5 will exist. So we can say that at x is equal to 3, right, the point would be continuous. Another way to test to see if a point is continuous is we look at the left and right-handed limits, right? So what is a left-handed limit? A left-handed limit is basically you're approaching the value of x from the left side. So we said that x is approaching 3. Well, basically you're approaching 3 from the far left side. So it's a value that is left of 3 that's very, very close to 3. Like an example would be if you're looking at approaching 3 from the left side, we can write x approaches 3 from the left side of f of x. Then x can be a value like 2.9999, right? And in this case, f of x will get closer and closer to 5, right? So basically, limits are written as x approaches a, y will approach another value L. Okay? So as x approaches 3 from the left side, y will approach 5. And we can also look at the right-handed limit. I'm going to do this in a different color. And in the case of a right-handed limit, basically you're looking at, if we're looking at 3 as our value of x, as x approaches 3 from the right side, f of x will also approach 5. Because 3 from the right side is, you can say that 3 from the right side could be like a value like 3.00001. So really the left and right-handed limits are just small increments either to the left or right of a certain value, right? So in general, limit as x approaches a of f of x is the left-handed limit, and limit as x approaches a from right of f of x is the right-handed limit. Okay, so this is the right-handed limit. You can use the left and right-hand limits to test to see if a limit exists, right? So how we can show this, I'm just going to erase this portion out. Oh. Right, so how we can show this, to show that a limit actually exists and a point is continuous, if the left-handed limit x approaches a from the left of f of x is equal to the right-hand limit as x approaches a from the right of f of x, then x approaches a is continuous. So when x equals a, it's continuous. It's a continuous point, right? So it's a continuous point of x. Now we also need to show that limit as x approaches a of f of x is continuous. And when x approaches a, f of x should approach f of a. And this guy should be a point that exists, right? L is a finite value. And L is a value that exists. Okay, so the criteria here is if the limit as x approaches a from the left side of a is equal to limit as x approaches a from the right side of a is equal to limit as x approaches a of f of x, which is equal to f of a, which is equal to L, then the point is continuous at x is equal to a. Okay, and I did the same thing with this point here, right? So when we looked at this graph and we looked at the point 3 and 5, I'm just going to erase this out, but I'm going to just take a look at this graph really quickly again, right? We wanted to show that x is continuous at 3, right? We can see that limit as x approaches 3 from the left side, and this is the left-hand limit, right, of this function. As x approaches 3 from the left side, basically that's equivalent to 5. Limit as x approaches 3 from the right side of f of x, and we said from the right side is going to be a value like 3.0001, and that's getting close to 5 as well. And limit as x approaches 3 from f of x is basically f of 3, which is equal to 5. So because limit from the left side is equal to limit from the right side of f of x, which is equal to the limit as x approaches 3 of f of x, and they're all equal to 5, therefore the point is continuous at x is equal to 3. So what that means is that the point 3 and 5 exists, right? And in order for you to determine if a point is continuous, you just test the limits of that point, the left-hand limit, the right-hand limit, and the original limit, right? And as long as that equals a finite value and they're all equivalent, then that point will exist. So I've summarized all of this material in this white box here, right? So that's what we showed here. If the right and left-handed limits, so this is the left-handed limit is equal to the right-handed limit, right? Then the point will exist, right? And if the original value, the limit of f of x as x approaches a is equal to L, and L is some kind of finite number, a fixed number, right, then the limit will also exist. And collectively, if all of these statements are true, right, if these statements as well as these statements are true, then the point is continuous. It's essentially what we just did here.